Hello students, next chapter, dual nature of matter and radiation. We know that light exhibits dual nature. So to explain some of the phenomena such as interference, diffraction and polarization, we considered that light exhibited wave nature. While explaining the phenomena such as photoelectric effect as well as Compton effect, we considered that light is exhibiting particle nature. That means light exhibit both wave nature as well as particle nature. Similarly, matter also exhibits both particle nature as well as wave nature. Next, electron emission. The liberation of electrons from the metal surface is called as electron emission. Depending upon the source of external energy, the electron emission process can be broadly classified into four categories. First one, thermionic emission. The liberation of electrons by a metal surface by supplying heat energy is called as thermionic emission. Next, the liberation of electrons by a metal surface when a strong electric field is applied is called as field emission. Next one is photoelectric emission. The emission of electrons from a metal surface when a light of suitable frequency is incident on it. Next one is secondary emission. When a fast moving beam of high energetic electrons incident on the metal surface, then electrons are liberated. That is known as secondary emission. Now we are going to discuss in detail about the photoelectric effect. So it is the phenomenon in which the electrons are liberated by a metal surface when light of suitable frequency is incident on it. The liberated electrons are called as photoelectrons. The corresponding current in the external circuit is called as photoelectric current. So next, photosensitive materials. Some materials respond even for ordinary light. That means even when ordinary light falls on some materials, the electrons are liberated. Such materials are called as photosensitive materials. Hertz observations. So while conducting his spark discharge experiment, Hertz observed that when light falls on certain metals, so electrons are liberated. Next, Havelock's and Reynolds observations. These two scientists study the photoelectric effect in detail. They observed that when UV light falls on the zinc metal, then what will happen? Electrons are liberated. So when no UV light falls on the zinc surface, electrons are not liberated. Next, work function. So the minimum energy required to liberate the electrons from the metal surface is called as work function. Work function is given by the formula W0 is equal to HU0, that is equal to Hc by lambda naught. Next, threshold frequency. The minimum frequency of incident radiation below which there is no photoelectric emission is called as threshold frequency. Similarly, the maximum wavelength which is just sufficient to liberate the electrons from the metal surface is called as threshold wavelength. Next, you studied about the experimental arrangement to study the photoelectric effect in detail in your regular classes. Next, factors affecting the photoelectric current. First one, intensity of incident radiation. We know that the photoelectric current varies in terms of intensity of incident radiation, in terms of collector potential as well as frequency of incident radiation. If you keep the frequency of incident radiation and collector potential constant, and as the intensity of incident radiation increases, the photoelectric current also increases. As the intensity increases, the number of electrons emitted by a metal surface increases, the number of electrons reaching the collector plate increases, and hence the photoelectric current also increases. So the next factor, the effect of anode potential or collector potential. By keeping the intensity of incident radiation and frequency of incident radiation fixed, if you increase the anode potential, then photoelectric current goes on increasing, and at a particular anode potential it reaches its maximum value, that is nothing but saturation value. So thereafter, even if you increase the anode potential, the photoelectric current remains same. Next, if you reverse the polarity of collector plate and the anode plate, then what will happen? The photoelectric current goes on decreasing, and at a particular value of anode potential, negative potential, then what will happen? The photoelectric current becomes zero. That potential is called as stopping potential or cutoff potential. The minimum negative potential that must be required to reduce the photoelectric current to zero. That is called as stopping potential or cutoff potential. So that is given by maximum kinetic energy of the ejected photoelectrons is equal to EV naught, where V naught is the stopping potential. From this, it is clear that the saturation current depends upon intensity of incident radiation, but it is independent of frequency. Why? The maximum kinetic energy of the ejected photoelectrons and the stopping potential depends upon the frequency of incident radiation and not on the intensity of incident radiation. Next, effect of frequency of incident radiation on photoelectric current. As the frequency of incident radiation increases, as I said earlier, saturation current remains same, but the stopping potential increases. Next, so as the variation of maximum kinetic energy of the ejected photoelectrons with the frequency of incident radiation. As the frequency of incident radiation increases, the maximum kinetic energy of the ejected photoelectrons also increases. So here mu naught is the threshold frequency. So for every given metal surface, there should be a minimum frequency of incident radiation below which there is no photoelectric effect. Next, Einstein's explanation for photoelectric effect. Einstein explains the photoelectric effect by using quantum theory. According to quantum theory, the emission or absorption of energy does not take place continuously, but in terms of discrete units. Such discrete units of energy are called as quantum. So here, according to Einstein's explanation, when light falls on a metal surface, that means the photons are incident on the metal surface. So the energy of the incident photons is transferred to the electrons present inside the metal surface. The electrons, after acquiring the sufficient energy, they ejected out of the metal surface. So here H is the energy of the incident photon. So a part of the incident energy is utilized as work function. The remaining energy is utilized as the maximum kinetic energy of the ejected photoelectrons. That can be written as h nu is equal to h nu naught plus kinetic energy maximum. That is, maximum kinetic energy is equal to h nu minus h nu naught. Or it can be written as half mv maximum square is equal to h into nu minus nu naught, where v maximum is the maximum velocity of the ejected photoelectrons. So that can be written as v maximum is equal to root of 2h by m into nu minus nu naught. So we know that maximum kinetic energy is equal to E into V naught, where V naught is the stopping potential. So that can be written as Hc into 1 by lambda minus 1 by lambda naught, or maximum kinetic energy is equal to Hc into lambda naught minus lambda divided by lambda into lambda naught. By using this, you can write expression for maximum velocity as root of 2hc by m into lambda minus lambda naught divided by lambda into lambda naught. Expression for stopping potential V naught is equal to h by E into V minus V naught, or hc by E into 1 by lambda minus 1 by lambda naught. So next, according to Einstein's photoelectric effect, according to Einstein's theory, the emission or absorption of light energy takes place in terms of discrete units. Such discrete units are called as photons. Energy of photons is given by E is equal to h nu, or E is equal to hc by lambda. So mass of the photon is given by m is equal to h nu by c square. The momentum of the photon is given by p is equal to h by lambda. So the number of photons emitted can be calculated by using the formula L is equal to p by E, that is equal to p by h nu, or p lambda divided by hc. So amount of energy crossing per unit area normally per second is called as intensity of light. Intensity of light is given by I is equal to E by AT, that is equal to P by A. The waves associated with the moving material particles are called as matter waves, which are also called as de Broglie waves. The wavelength associated with the de Broglie waves are called as de Broglie wavelength. De Broglie wavelength is given by lambda is equal to h by p, or h by mv, that is equal to h by root of 2me. So for a charged particle such as electron, the de Broglie wavelength is given by lambda is equal to h by root of 2me, that is equal to h by root of 2m into q into v. And the experiment which confirms the wave nature associated with the electron is Davison and Germer experiment. Thank you.